Hello everyone, welcome to the course on Signal and System. This is lecture 1 and in this lecture we will see the brief idea about the continuous time systems. So, a continuous time system, we have seen various type of properties, or we can say the type of systems. So, the systems are classified as we can say static dynamic, causal non-causal, linear non-linear, time variant invariant, and similarly we have invertible and non-vertible. So out of those type of system, we are just selecting the linear as well as time invariant. So what is linear systems? A system is said to be linear if it follows principle of superposition, and the principle of superposition consists of additivity plus homogeneity. So let's say if we have x1 and x2 are the input signals that is applied to a system, and basically that system is characterized by some function, let's say, and it will give rise to y1t and y2t. So what this linearity says, what this principle of superposition says, it says that the system applied on the input signal x1 and x2 will be giving rise to y1 and y2, which is y1 plus y2. So overall, we can say the linearity which consists of homogeneity, a times of x1 will give rise to a times of y1. Similarly, b times of x2 will give rise to b times of yt. So this is called as homogeneity. So as a whole, additivity plus homogeneity is known as principle of superposition. So whenever a system is following these two things, then the system is said to be a linear system. Whereas the second type of system, what we have is called as time invariant system. So what is time invariant system? A system is said to be time invariant if a time shift in the input signal results in an identical time shift in the output signal. If this is a situation, then we can say that the signal is said to be time invariant. Otherwise, we can say the system is time variant. So again, there is a procedure that how we can check the time invariancy of a system. So if we are performing a shift in the input signal, and after that we are applying a system onto that, so definitely it will give rise to y of t minus t naught. So at this particular stage, we are able to find out that whether a system is linear or non-linear. Also, we are able to find that the system is time variant or invariant. So we are taking both the properties, both the type of system over here, and we are just making a LTI, linear time invariant system. In most of the applications of control system in the DSP, we are basically assuming, initially we are assuming that the systems are linear time invariant. So now the point is, what is the use of, why we are studying only this linear time invariant systems? So in engineering, we can say that the LTI systems play a very important role. Very powerful mathematical tools we are having for the development and the analysis of LTI systems. So that's why we generally study these LTI systems. Also, LTI systems are much easier to analyze rather than the other which are not LTI. Similarly, in practice, systems that are not LTI can be well approximated. They can also be approximated using a LTI model. So even when dealing with the systems that are not LTI, the LTI system still play a very important role. So that's why we are studying here the LTI systems. So now what the next question is, let's say we have a system, and the system which is having an input x of t, let's say, and the impulse response of the system is denoted by ht, and the overall response of the system is denoted by yt. So how these input and impulse response is correlated, how they are interconnected? We can say that the output of any LTI system can be obtained with the help of a tool called as convolution, and yt equals to xt convolution with ht. This is a mathematical operator. So this asterisk sign is nothing but a symbolic representation of convolution. So first of all, we will be having a definition of impulse response. What is the impulse response? So the basic definition here is that when the input signal xt is an impulse signal, so the response, the output of a system is called as impulse response. Later on we will see that what is the definition for step response. So likewise we have a definition for step response also, that when xt is a unit step signal, right? So the output yt can be denoted as st, and st is a representation for step response. So we can calculate st as h of t multiple h of t convolution with u of t, because instead of xt I will be having a unit step signal. So the convolution basically which results in x of t convolution with h of t at the point t is simply a weighted average. It's a weightage average of the function x, where the weight is given by h times reversed and shifted by t. We'll see later on what are the operations involved in performing a convolution. So here this asterisk symbol will always be used to denote the convolution, not multiplication. It's not a normal multiplication. Multiplication is a part of convolution, but it's not exactly, we cannot say convolution is exactly a kind of a multiplication. So convolution is used extensively in system theory. In particular, convolution has a special significance in the context of LTI system. Means for a LTI system, if you want to calculate the response of a LTI system, we generally use a mathematical operator or a tool called as convolution. So if we have a, let's say, if we imagine that we are dealing with a continuous time LTI system, so we'll say that we are dealing with convolution integral, and whenever we have a discrete time system, so we'll say that we are dealing with the convolution summation. So that is the only difference between the discrete and the continuous time systems. Now how we can perform the convolution? What are the basic steps in performing the convolution? So what we have let's say x of t convolution with h of t is nothing but minus infinite to infinite x of tau and h of t minus tau d tau. This is a mathematical way of representing the convolution. Also, this can also be written as minus infinite to infinite. We can interchange. Later on we'll see what are the properties of convolution, and with the help of those properties I can write x of t minus tau h of tau d tau. Later on we'll see the this commutative property of the convolution. We can interchange x of tau with h of tau. So how can we start? So first is, if we will use this particular equation to perform the convolution, so first is we'll be plotting x of tau and h of t minus tau as a function of tau. Here now the variable is nothing but tau. Previously we have a variable as t, but now the variable is shifted and that is now changed to tau. So the important thing is how we can make h of t minus tau from h tau. That is the point. So initially there are certain steps. H of t minus tau can be written as h of minus tau plus t. So how we can initiate h of t? First we can have h of tau. From h of t we can have h of tau. After that, with the help of shifting, I can have h of tau plus t, and finally with the help of time reversal I can have h of minus tau plus t, which is nothing but h of t minus tau. So both are the same thing. So these are the steps. Means first we'll be having a variable, change of variable. After that we have we call as time shifting over here. After that we call as time reversal over here. So these are certain steps which are used to plot h of t minus tau. So once we have the plotting of x of tau and h of t minus tau. Now we need to perform we need to just multiply these signals x of tau and h of t minus tau, and we just find out the area under the curve. So here what we have, we just writing the mathematical expression for x of tau, x of t convolution with h of t will increase t gradually until the expression for xt convolution with ht changes form. Record the interval over which this expression was valid. We have to find out the range for the value of tau, for which will be able to find out the area. So now we'll be using this convolution, the method of this convolution, to perform the response of a system. So to elaborate this, we have a numerical over here, which is find the convolution of two continuous time signals. We have x of t e raised to power minus mod of t for all t, and h of t is e raised to power minus 2t, which is valid for t greater than 1, and also it is 0 for all t less than 1. So what are the steps? First step is we'll be plotting xt and h of we can say x of tau and h of t minus tau. So mod of t, if we'll see the definition for mod of t, the value is minus t for all t less than 0, and it will behave as a positive t like this. So if we want to draw x of tau, so e raised to power minus t, and also we have minus outside, so it will become what? E raised to power plus t. Likewise, whenever tau is less than 1, so we will be having a curve like this. This is a curve for e raised to power tau, and this is a curve for e raised to power minus tau. This is, let's say, 0. So this is a plot for x of tau. Now h of t, if we can see h of t, how we can start? H of tau, again it will start from 1 onward, and e raised to power minus 2t, so it will be, the value keep on decreasing as t approaches towards infinity. So how we can start? We want h of t minus tau. So first step is we'll be making h of tau plus t. So I can have, I'll be shifting this. This is 1 minus t like this. Now the reversal part. So I can have something like this, t minus 1, this is tau, and this is h of t minus tau. Clearly we can see that we have h of t minus tau over here. Now we can see over here that we want to perform the convolution. So convolution means yt is nothing but x of t convolution with h of t. This can be represented as minus infinite to infinite x of tau h of t minus tau d tau. We have performed the shifting as we have performed h of t minus tau. We have also x of tau. If I can draw with the cases, let's say, what I can say, t minus 1 is less than 0, means we have a curve and this is t minus 1 h of t minus tau. This is the first case. The second case will be when the scenario is t minus 1, again this is h of t minus tau, and here we have tau. So this is a condition when t minus 1 is greater than 0. Later on we'll see, since it is a continuous kind of a waveform, so I can add equality. So as we can see, t minus 1 is less than 0, and I'm going to multiply these signals x of tau and h of t minus tau. So here we can pen down the case 1 when t minus 1 is less than 0, and the output yt can be solved as, if we can clearly see what is the common region over here, what is the common values of tau over here. So it will be from 0 to t minus 1, sorry, minus infinite to t minus 1, and the signal over here, the signal is e raised to power tau, and here this is e raised to power minus 2 t minus tau. This equation I can write down e raised to power minus 2 t minus tau and d tau, like this. So our aim is to simplify this expression for our very first case, which is t minus 1 less than 0. Later on we can simplify this inequality also. The second possibility is when t minus 1 is greater than 0, or we can have equal to also. So if we just superimpose this h of t minus tau on x of tau, so we can clearly see the region will be from minus infinity to t minus 1, but the integration limits will be break down in two parts. One is minus infinite to 0. So we can note down the case 2 when t minus 1 is greater than equal to 0, which is t is greater than equal to 1. This is a condition for 3. Now this yt can be represented as the summation of two integrals. One is from minus infinite to 0, and the next is from 0 to t minus 1. So what was x tau in our previous figure? X tau to the left was e raised to power tau. So I can now write e raised to power tau over here, and the h of tau is e raised to power minus 2 t minus tau d tau. This is the first integral, and the second integral is now 0 to t minus 1, this particular region. The x of tau is nothing but, it can be represented as e raised to power minus tau, also e raised to power minus 2 t minus tau d tau. We can clearly solve the integration for both the possibilities. So we'll be having the output yt. First case, when t is less than 1 and when t is greater than equal to 1. Two possibilities. We'll be having the output yt for both the scenarios. So if we can see further, you'll be having a output yt, which is for t less than 1, the output is 1 by 3 e raised to power t minus 1. We can clearly find out this with the help of this integral, as we can see that this will be minus infinite to t minus 1. This is e raised to power 3 tau d tau. Also we'll be having e raised to power minus 2t outside, because it is independent of tau, and just put the limits over here. So e raised to power minus infinite, that definitely it will become 0, and what you are having, you will be having e raised to power minus 2t outside and e raised to power 3 t minus 1 whole divided by 3. So e raised to power, clearly you will be having a same answer, 1 by 3 e raised to power t minus 3. Similarly, for t greater than equals to 1, we need to solve this particular integral. Let me write down, this will be minus infinite to 0 e raised to power 2 tau d tau e raised to power minus 2t outside plus the second integral 0 to t minus 1, this is e raised to power tau d tau and e raised to power minus 2t outside. So we have these two integrals, we need to solve these integrals further and we need to put the values of tau and we'll be getting a result which is this one yt. So we can clearly see that yt, we get output, we get the response of the system for all possible values of t, which is for t less than 1 as well as we are getting a result for t greater than equals to 1. So this figure basically is the representation of our response yt. As we can see that when we have t less than 1, the response is calculated or plotted as per this equation, and whenever t is greater than 1, so the response is basically I am getting from this particular equation. So this is a proper way of computing the response of a LTI system with the help of an operator called as convolution. Now we have certain properties of convolution. So these important properties which we are going to use while we are performing a convolution summation or a convolution integral. So the first property is called as commutative property, means if we have x of tau or x of t convolution with h of t, so we can interchange. We can have h of t convolution with x of t depending upon that which signal is a complicated one. So the complicated signal one, we need to avoid shifting or reversal in a complicated kind of a signal. Whichever signal is easiest one will be making h of t minus tau. This can also be written as, we have already seen, minus infinite to infinite x of tau multiplied by h of t minus tau d tau, and this is also equals to minus infinite to infinite x of t minus tau and h of tau d tau. This is called as commutative property. Now we have the second property which is called as associative property. So what we are seeing over here is that if we have some xt convolved with h1 of t, and after that the entire result of this convolution is performed with the next impulse response, which is, let's say, h2t. So what we can perform is, we can first compute the convolution of h1 and h2, and after that whatever result I am getting over here, the result will be convolved with x. Now the last is the distributive properties. So basically this associative and distributive property, they came into picture when we have let's say the cascade realization, and whenever we have a parallel kind of a realization. This is cascade, means if we have h1t like this, we have h2t like this, so the overall impulse response is nothing but h1t convolved with h of t. Whereas at distributive property, we generally use this when we have a realization called as parallel realization, like this. So here what we can see, that the overall impulse response of the system will be nothing but the addition of two, like this, h1 and h2. So I can have x convolved with h1, x convolved with h2, and I can perform the addition over here. So this is called as these are called as the properties of the convolution. Later on we'll see the convolution summation. So convolution summation is basically performed when we have a discrete time system, when xn and hn both are discrete. So the convolution is performed, that is known as convolution summation. So these are the references, and in the next lecture we'll see the discrete convolution, and later on we will see some examples both based on continuous time convolution and the discrete time convolution.